Alright, so in this video we'll focus our attention on p-series, which we derived in the last video by the integral test. But the result is just this. The sum n equals 1 to infinity of 1 over n to the p converges if and only if p is larger than 1. So the borderline case would be p equals to 1, which diverges. That's the so-called harmonic series. Alright. So as my first example, as you can see, sum n equals 1 to infinity of 1 over n is p equals 1, which is not larger than 1, and therefore S diverges by the p equals 1 series test. In other words, by the way, this is called the harmonic series. Moving along here, p equals 2 series is 1 over n squared. Oh, wait a minute, this is almost, hold on a second, I wasn't looking carefully enough. This is n equals 3 to infinity. Oh no. That's almost a p equals 2 series, almost. Now if I was to add 1 and a fourth, then I would have the honest to goodness p equals 2 series, which converges, right? So if I have the series I'm after plus 5/4 converges, then you know what? The series converges. So in fact, since I happen to know that that series converges to pi squared over 6 by math magic, the given series would be convergent to pi squared over 6 minus 5/4. So here's a bit of intuition for you. The convergence and divergence of a given series is really only dependent on the tail of the series. So there's a kind of souped up version of the p-series, which a lot of people would still say is just a p-series. Sum n equals n naught to infinity of 1 over np converges if and only if p is greater than 1, where n naught is just some fixed natural number. It could be, my example 2 was 3, it could be 333, it could be 3 trillion. It wouldn't matter. It doesn't change anything. Any finite starting point, it's all about the p, all right? So here we go. Sum n equals 13 to infinity of 1 over the square root of n is almost a p equals 1/2 series, but 1/2 is less than 1, so this diverges by the p equals 1/2 series test. All right, so I'm gonna allow you that terminology, all right? So here we go. We're looking at a series of a sum, which is the sum of the series, provided, of course, that these actually converge, and they do, because this is a p equals 3 and this is a p equals 1.5 series, which both converge by p-series test. Again, this step is only allowed because the right-hand side series both are convergent. And so, by the way, there's a theorem that we have about taking series and splitting it apart. If we have the sum of an or bn is divergent, then the sum of divergent series is again divergent, provided, this is important, I'm assuming that they're both positive, or rather non-negative series. If one of them was positive and one was negative, it's possible that when you add them, you could take divergent things and convert it to convergent. Anyway, and by the way, this notation, not writing the starting point, it's assumed that such series go to infinity and that the starting point is irrelevant to the question at hand. So this notation is sometimes used in such a context. But if you're using it, you better have a good reason for it. So, all right. Here's one. This diverges since these are both positive, and that's a divergent. This is a divergent p-series. Now that's convergent because p equals 3, but convergent plus divergent, both of them being non-negative, they do blow up. All right. Alternatively, of course, you could just do what? You could just use the nth term test, right? Because if you look at the a sub n over cube root of n over 1 plus 1 over n cubed, that goes to infinity, which of course is not equal to 0, as n goes to infinity, so that series fails to converge. This series fails to converge by the nth term test. Here's one 3 over n cubed, we can pull the 3 out, and we have 3 times the p equals 3 series, again converges by the p equals 3 series test. So I tried to show you some slight variations on just basic p series. We could start at a value beyond 1, we could sometimes add them, we could multiply them by a number. There's a few different minor variations on this theme we could do and still really be, in my view, looking at a p series. Well, that's it for this one. Thanks, guys.